record on the... Okay, so we are answering kind of a conceptual question about what's the relationship between diagonally dominant and invertible. And there's this little theorem in the book about recognizing an invertible matrix that then goes on to reason that diagonally dominant matrices are invertible, right? You guys with me on this? Is words that appear in the book. Okay, so now when they say diagonally dominant matrices are invertible, the logic that we should be concerning ourselves with is that we have this situation where we know that dominance implies invertibility. Okay, and just like mathematically reasoning wise, that also means that not invertible implies not dominant. Okay. So we have these two statements. These are the two statements that are claimed in the book. Now there's this kind of other thought, which is that maybe invertibility implies diagonal dominance. Does that make sense? Like if diagonal dominance implies invertibility, maybe those are the same concept. And in this case, that's not true. So just because a matrix is invertible doesn't mean it's diagonally dominant. Does that make sense? Mm-hmm. So let's see, could we come up with a matrix that is invertible but not diagonally dominant? Right, so my kind of claim is that the converse of this statement, which would be that invertible implies dominant, that this is not true. You guys with me on that? Okay, so in order to demonstrate that, I would probably need to come up with a matrix that is invertible, but not diagonally dominant. You guys see that? I only need one example. Mm-hmm. Good. Yes, no, maybe, or yeah?
Yeah.
Okay, so first, where would I go to start finding one of these? Like, what's your go-to to start building an example of a matrix at all?
The identity matrix?
Yeah, good. Start with identity or start with zero. You probably always want to do one of these two things. In this case, I'm probably going to start with the identity matrix and not the zero matrix. Why?
Because
why wouldn't I want to start with the zero matrix?
Because its diagonals are zero.
Yeah, it's like, I'm not even really sure what diagonally dominant would mean there. And also it's not invertible anyways, right? I need to start with an invertible matrix. So, okay, so I'm going to start kind of reasoning with 1, 0, 0, 1. Okay, is 1, 0, so is the identity matrix, instead of reading this thing like a fool, is the identity matrix invertible? Yeah. Is it diagonally dominant?
Yeah.
Oh, shit. Okay, so this didn't necessarily work, right? This didn't support my claim. It also doesn't really contribute evidence against my claim. It just didn't work. You guys see that? Okay, so that one's not going to be the counterexample I'm looking for. Is there another kind of related thing that I could use? What is it that I need to have happen here? I need to get the diagonal entries smaller and the other entries bigger, right? In order to have this not be diagonally dominant. So how can I make the other entries bigger and the diagonal entries smaller without losing my invertibility?
I was going to say, like, literally any elimination matrix would probably be invertible, so you could just like...
Yeah, I mean, that's a thing we know, that elimination matrices are invertible.
So you could just make like one of the zeros a larger number than 1.
Yeah, so I could go with an elimination matrix like 1, 0, 2, 1, right? how do I know this thing is invertible? What are you checking for invertibility? This is actually a really hard question. I don't know if you guys have you noticed that in the very back of the book here?
Isn't it that you're checking to make sure it has a right amount of pivots?
Yeah, that would be one way to check. I could check the pivots. The thing I'm trying to point to is that in the back of the book, page 573, there's a whole crap ton of different characterizations of invertibility back there. And the reason for that is that this is really the fundamental question of linear algebra. It's like, does this function have an inverse? And so there's a lot of different ways for me to sort it. One thing I could do is I could look at this matrix and see that the pivots are 1, right? And so I could see that this thing is probably invertible. Another thing I could do is I could calculate the determinant. Another thing I could do is ask the computer to invert it, see what it gives me. All of those are valid options. I could do elimination on it to manually calculate the inverse. Like, you've got lots of options for this. Feel free to use any one of them under the sun. Doesn't matter to me. All I need, though, is that this matrix is invertible. Check for some reason, right? In my case, I'm just going to take the determinant, realize the determinant's 1. And it's also not diagonally dominant. Okay, so this thing is proof that invertibility does not imply diagonal dominance. Does that sort of answer your question, Jake?
Yeah, I think that does. I think it was just because the textbook stated that C is singular, and that just confused me because I was like, well, that's not even in the proof. So are they stating that, like, if it's not dominant, it's singular?
Yeah, so if it's not invertible, then it's not diagonally dominant,
Yeah. Okay.
Yeah, this is something that screws people up pretty consistently. So we have a statement here, diagonally dominant implies invertibility. And then we have that statement's contrapositive, which is this not invertible implies not dominant. And that really amounts to the same statement. Those two statements are logically equivalent. And then there's this other thing, which is the converse, which is essentially the opposite of our statement, which may or may not be true. Does that make sense? Should I write those down? Maybe let me write those down. Okay, so we have a statement, P implies Q, right? That statement has a contrapositive, which is not Q implies not P. These two statements are equivalent. This is separated from the converse, which is to say Q implies P. And this is essentially the logical opposite, although that's not really fair. But in some sense, this is kind of the opposite of the original statement. So this is not equivalent. And oftentimes a separate and interesting question. You guys with me on this? Okay. There's a sort of a classic. Never mind. I hate the Raven thing. Forget it. If you want to look up a kind of a classic philosophy of science argument, there's I think it's Hemdall's Raven. If you feel like doing some research on this and twisting your head around a little bit, take a look at the Raven paradox. It's kind of interesting. All We'll call it for that.